Good evening, Loughton. This is Gaia, and you can see there its 5-year mission was to map 1 billion stars. It did that so well, they changed its mission to a 10-year mission to map 2 billion stars. So I'm going to tell you this evening about why we bother mapping the stars in the Milky Way, how they can be mapped accurately, what type of data we can get, and what do we hope to learn from the data. So let's start with why do we map the stars in the first place. I guess a lot of you have either got a paper atlas or perhaps an electronic atlas on your phone, and it's a simple enough question: where are the stars? And of course we want to be able to map them on the sky so that we can find them again later and tell if things have moved, or to find if a new object has appeared in the sky. But what I'm really talking about this evening is mapping the stars with very high precision. Because if we can determine the three-dimensional mapping of where the stars are, then we can get a better understanding of the structure and ultimately the evolution, the history and the future of our Milky Way galaxy. So how do we map the sky? Do we just take lots of pictures and stitch them all together? Well, of course that works fine for mapping the Earth, for instance, from a satellite in space, but there's a problem doing that on the stars in the sky, and the problem is the stars move. They don't seem to move that fast when you think about stars moving in the Milky Way, but nothing in the galaxy is actually static. Not the Earth going around the sun going around the Milky Way, or all of the other stars in the Milky Way moving in their own independent orbits. So if nothing is static, you can't simply take a whole load of pictures and stitch them together. And the second reason you can't simply do that is because that wouldn't give you the three-dimensional positions. Knowing the positions of stars on a two-dimensional sky is not enough if you want to map out what the Milky Way is doing. If we remind ourselves, for instance, that there's the familiar constellation of Orion as seen from Earth, but actually all the stars in the familiar constellation are all at different distances. And so knowing the two-dimensional mapping is simply not sufficient. We need to know their distances. And bear in mind that we want the distances not only so that we can figure out what the structure, the full three-dimensional structure of the Milky Way is. We actually need to know the distances simply to understand the stars themselves. Because if you think of mapping out stars in the familiar HR or Hertzsprung-Russell diagram, where we plot the luminosity of a star on the vertical axis and the colour of a star on the horizontal axis, without knowing the distance to a star, we can't determine its luminosity. In other words, we can look at a blue star, but if we don't know its distance, we don't know whether we're looking at a very bright star that's a long distance away, or a very dim star that's very close. Is it a blue supergiant or is it a white dwarf? And similarly, if we're looking at a red star, how do we know whether we're looking at a red supergiant or a red giant or a red dwarf? Yes, we do get clues from the spectrum of a star, but really we need to know its distance so we can pin down absolutely what its actual luminosity is. And also bear in mind that if we don't know the type of star that we're looking at because we don't know its distance, then we actually don't know much about any exoplanets that might be orbiting that star. Because if you think of the techniques that are used to find exoplanets, we always find the size of an exoplanet relative to the size of its host star. And we find the mass of exoplanets relative to the mass of their host star. So if we don't know the actual luminosity or the actual type of star we're dealing with, then we actually know very little about the exoplanets that are orbiting it. So we need distance for understanding stellar systems, stellar evolution, and we also need it to help us understand exoplanets as well. But the main thrust of what I'm talking about is getting a full three-dimensional map of the Milky Way so we can understand the dynamics of the Milky Way itself. So distance is important. How are we going to get distance? Well, perhaps you're already familiar with the idea of parallax, the apparent change in the position of an object due to the motion of the Earth around the Sun, as indicated by that diagram on the right. And it's often described as a nearby star will move relative to fixed stars in the distance because of parallax. You're familiar with this idea. If you hold your finger up and blink your eyes, your finger appears to move relative to background objects. But this rather naive way of thinking about parallax always assumes that there are fixed stars in the background that will help you tell if a nearby star appears to move as the Earth goes round the Sun. There's the parallax angle we're dealing with. It's nowhere near as large as this cartoon would indicate, because remember that stars are very distant compared to the distance of the Earth-Sun, 1 astronomical unit. The distance to stars is many millions of times larger than the distance between the Sun and the Earth. So in fact, this triangle is a very slender triangle, and that is a very small angle. But the real problem, one of the real problems, not only the fact that the parallax angle is small, is the fact that there's no such thing as a fixed star, in the sense that nearby stars will move relative to more distant stars, but they are also going to appear to move because of the Earth moving around the Sun. All stars in the Milky Way will appear to move. Now, in terms of distances, if we think of a star 3 light years away, that would have a parallax of 1 second when we work out the maths and the size of this triangle. And any star at a distance of 3 light years with a parallax of 1 second, we call that distance 1 parallax second, or 1 parsec for short. 1 parsec is about 3.26 light years. Remember, the nearest star is actually 4 light years away, therefore there are no stars as close as 1 parsec. So all stars will have parallax angles of less than 1 arc second. And if a star is thousands of light years away, it will have a parallax angle that is 1,000 times smaller than that. So here's the crux of the problem. If we want distances using the parallax, the apparent change in position as we go around the Sun, well, we need parallax to determine distance. But parallax needs the actual position of the star in the sky, not simply the position of one star relative to another star, which might also appear to be moving because of parallax. Not only that, but the stars themselves are moving. They are moving around the center of the Milky Way, so-called proper motion. So we have these multiple problems. We need parallax, but parallax needs absolute positions on the sky, and we have to take into account the fact that the stars themselves are moving. This is why mapping the stars in the Milky Way is not a trivial task, and this is why it couldn't be done many, many decades ago. We needed certain levels of technology to allow us to be able to do this. So how do we map accurately? If we want to untangle the apparent motion because the Earth is going around the Sun, producing the parallax that I've just described, as well as the fact that the stars have proper motion as they move in the Milky Way, we need high precision measurements and we need a fixed coordinate system. We need high precision measurements because the parallax angles are very small. Remember, 1 arc second is a ridiculously large parallax angle. We're talking about parallax angles that are many, many orders of magnitude smaller than that. And because not only the Earth is going around the Sun, but also the stars themselves are in motion, we need to think very carefully about the coordinate system we're going to use to make sure that we can accurately determine the motions of stars. Just as a little bit of an aside, back in the 1980s it was thought, why don't we make this job easier by making the baseline of the parallax triangle larger? Instead of having 1 astronomical unit, the distance from the Earth to the Sun, let's send a spacecraft out 1,000 astronomical units into the solar system to have a much bigger baseline to make the parallax angles bigger and hence easier to measure. Bear in mind it would have taken 50 years to fly a spacecraft out that sort of distance. Remember, even Voyagers have only got to about 150 astronomical units. So even if this plan had gone ahead in the 1980s, that spacecraft would not be on station yet. It would still be on its way out towards the 1000 AU point. So this idea of making the parallax angles larger never actually happened. Instead, we waited until the technology was able to measure very small parallax angles. So what coordinate system should we use to map the stars? That might sound a bit trivial. I mean, surely we know that when we look in a star atlas, we can measure the positions of stars using right ascension and declination, coordinates that use the celestial equator as a reference. So we have the north and south celestial pole, where the Earth's poles are pointing, and the celestial equator, which is a projection of the Earth's equator. Star atlases have been giving us right ascension and declination for a long, long time. Ever since the first Astronomer Royal, in fact, we've had RA and DEC as our coordinate system. Why is this coordinate system not good enough for what Gaia wants to do? If you think about an atlas where we have grid lines that tell us right ascension and declination, think about the star atlases that you might have now or have had in the past. For instance, when I was growing up, Norton's Star Atlas 1950 was the de facto standard. Now Norton's Star Atlas 2000. These aren't the publication dates. These are the epoch dates, the dates at which the coordinates of the stars are given and mapped and catalogued. Why does it change? Because the Earth's axis is continuously changing. The Earth's axis precesses. So the point on the sky that we define as the north and south celestial poles are continuously changing. And of course, the equator is changing as well. So even if we knew precisely the right ascension and declination of a star, it would change a second or two later, only by a small amount, but it would continuously change. And therefore, any coordinate system based on what the Earth is doing is not what we would call a fixed coordinate system. So you might say, okay, if the Earth isn't good enough, let's go and think about the Sun as a reference. Let's take the Sun as a fixed point and then think about where the stars are relative to that. But even that would lead to a small error, because the Sun is not, technically speaking, the centre of the solar system. If we think of where the Sun is, it actually moves around the centre of mass of the solar system. In this animation, it's slowed down just to show us that in the next few years, the centre of mass, the barycenter of the solar system, actually falls inside the Sun. But if we think of what was going on a few years back, the Sun was quite distinctly to one side of the centre of the solar system. That's because Jupiter and Saturn happened to be on the same side of the solar system and effectively were counterbalancing the Sun. So when we think about the centre of the solar system, the so-called barycenter, remember the planets technically do not orbit the Sun, although we often say that as a reasonable approximation. The planets don't orbit the Sun, they actually all orbit around a common centre of gravity, or barycenter. And the best coordinate system that we can use is based with the barycenter as the fixed reference point. In other words, all of the positions of the stars as if they were seen from the centre of the solar system. That's the coordinate system that Gaia generates. So if we think about what the sky actually looks like, here somewhat exaggerated, all the stars will appear to move in circles. Big circles if the star happens to be very close to the Earth, small circles if the star is a long way from the Earth. Maybe it's not a circle, maybe it's an ellipse, depending on where in the sky we happen to be looking. But all of the stars will be moving. And if we take into account the fact that they each have their own so-called proper motion throughout the Milky Way, then the actual motion on the sky will be more like a corkscrew. It'll be a combination of the parallax circular motion, depending on distance, as well as the general drift of the star across the sky due to its motion throughout the Milky Way. In other words, what we really want to measure is the corkscrew motion of every star in the sky that can be seen. If you can measure the corkscrew accurately enough over a long enough period of time, then you can effectively untangle the idea of a linear motion due to its motion around the Milky Way. Over a period of a few years, they will all look approximately linear. We're not going to be watching these stars for millions of years, of course. It'll be an entanglement of that linear motion and the circular motion due to parallax. So if we can measure all of these corkscrews, then we can work out what the stars are doing, which is important for trying to work out how the Milky Way is behaving. And it will give us the parallax because of the size of the circle will tell us how far away the star is. That'll again give us a three-dimensional model of the Milky Way, as well as giving us the absolute luminosity of stars, helping us with our understanding of stellar evolution. The first satellite that tried to do this was Hipparchus. Its name is there at the top. It was a homage to the Greek astronomer Hipparchus, the founder of geometry. Back in the 1990s, it was doing its stuff and measuring something of order 100,000 stars, the parallax of 100,000 stars, determined with a precision of order 1 milliarc second, 1,000th of an arc second. It did this for a whole range of stars down to a magnitude of approximately magnitude 12. And the Hipparchus catalogue, once it was complete, was used by, for instance, the Hubble Space Telescope to make sure that the Hubble was pointing in the direction it thought it was, with a precision of order milliarc seconds. So Hipparchus did a fantastic job back in the 1990s. Gaia is effectively a refinement of that idea. Now, the actual acronym for Gaia, let's not worry about what the acronym means, because they originally thought it might be an interferometer, and then later they decided it wouldn't be an interferometer. It's a different design, but they decided they liked the name. They thought that was pretty cool, calling it Gaia, so they kept the name. Gaia's mission was to improve on Hipparchus's ability to determine parallax. And the idea was Gaia was going to measure not 100,000 stars, but at least 1 billion stars, not with milliarc second precision, but with a precision of order 10 microarc seconds. And of course, a microarc second is 1,000th of a milliarc second. The higher precision of Gaia compared to Hipparchus meant that you could measure parallax at much greater distances. Remember the parallax angle and the parallax triangle. The greater the distance with a given baseline, the smaller the parallax angles. So with greater precision, you can effectively measure distances further out into the Milky Way. So the Gaia reach, if you like, would be much larger than that of Hipparchus. Not only that, it was also able to measure much fainter stars, not down to magnitude 12, but all the way down to something like magnitude 20. It's difficult to really get a handle on what 10 microarc seconds really means. Perhaps some of us have got this idea that some telescopes, if you're lucky, have a resolution of about an arc second. But what does 10 microarc seconds really look like? As a simple analogy to give us an idea of what we mean for the precision that Gaia is able to achieve, let's think about 10 microarc seconds as the ultimate resolution. That's equivalent to the thickness of a human hair as seen from a distance of about 1,000 kilometers. Imagine you're standing at Land's End and you're looking at a person in John O'Groats. Gaia, in principle, can measure the position of that person to an accuracy of the width of a human hair. That is a phenomenal ability. And that is why Gaia data is so incredible. Gaia as a machine is able to achieve these levels of precision. So you could ask, do we really need a new telescope? Don't we already have telescopes that are fantastic? Couldn't we use the Hubble Space Telescope? Isn't that an incredible telescope that's able to measure very accurately with very high precision? Don't we have already the Simonyi telescope, the LSST as it used to be known, currently located in the Vera Rubin Observatory? Isn't that able to map out billions of stars? Well, individually, these two telescopes are fantastic at what they do. The Hubble Space Telescope has got pretty good resolution, better than a milliarc second. And the Simonyi telescope can indeed map billions of stars. But the precision of the Simonyi is only of order hundreds of milliarc seconds, and the number of stars that the Hubble Space Telescope has measured the parallax for is only of order 1,000 or so. So if you wanted to do a survey of 1 billion stars, well, yes, the Simonyi could do that in 10 years, but with rather limited resolution. And if you wanted the Hubble to map out 1 billion stars? Well, yeah, it could do that, but it would take thousands and thousands of years, and we don't think the Hubble is going to last that long. So no, there are no existing telescopes that can achieve what we want from Gaia. So how does Gaia do what it does? Gaia is an ESA machine, an ESA spacecraft, or an ESA telescope if you like. The optics were produced in France and Germany, and a lot of the instrumentation, some of the power systems were made in the UK, the detector was made in the UK, and everything was brought together in the company called Astrium, which ultimately produced the final integration of all the components which were manufactured scattered across various European countries. Astrium is now part of Airbus. So it was constructed between 2006 and 2012 and launched in December 2013 and placed into a halo orbit around Lagrange point L2 in January 2014. So there it is on the right hand side there. L2 is that point 1 million miles above midnight of Earth. A sun shield blocks the light from the sun and the Earth and the moon. I'm not going to go into any details about L2. I covered that in an earlier talk. It's not rocket science. So the sun shield, just like the sun shield for the James Webb, is rather important to block the unwanted light from the Earth and the moon and the sun. And it was tested, tested in Toulouse in the Astrium factory here, and we can see this time lapse of checking that the solar shield unfurls as intended. It also gives you an idea of the scale of Gaia. You can see the sun shield is many meters in diameter. Some of the images of Gaia make it look rather small, but actually it's a relatively large spacecraft. So, how did it achieve micro-arc-second precision? We know that large telescopes give us high resolution and small mirrors give us poor resolution. So does that mean if we want a resolution that is significantly better than, for instance, the Hubble Space Telescope, we need to have a mirror that is kilometers in diameter or so? Well, clearly not, because we've just seen an image of what it actually looks like. It's only a few meters in size. In this graphic, we're comparing the sizes of various telescopes to scale. Right at the top there is the largest telescope in the world that's currently operational, the Gran Telescopio Canarias on La Palma. It'll soon be overtaken by the extremely large telescope in the bottom right there. But if we look at the space telescopes in the bottom left, let me just make those a little bit bigger so you can see them a little more clearly. You can see that the Gaia mirror, they happen to be rectangular, is no bigger than something like Kepler and is actually smaller than the Hubble Space Telescope mirror or indeed the James Webb Space Telescope mirror. So even though Gaia mirrors are smaller, how does it achieve this phenomenal resolution for measuring the positions of stars? Well, it achieves that through an ingenious combination of the instrumental hardware that it uses and the way it uses that hardware. The mode of operating is rather unlike any other space telescope. So firstly, let's just have a quick look at the hardware. The detector is a detector array of CCD sensors, over 100 of them, each of which is 9 megapixels. And together that gives you nearly 1 billion pixels of resolution in the detector. I'll say more about that shortly. And although I described Gaia as a telescope, technically it's two telescopes. Two telescopes are looking simultaneously, imaging different patches of sky, a little more than 90 degrees apart. And here's the clever bit in terms of its operation. Both telescopes create images on the same detector. That might seem crazy. Why on earth would you have two telescopes and not have two detectors? Why have you got two telescopes that are producing star images on the same detector? Gaia spins. The star images drift across the detector So Gaia does not take images. Unlike just about every other space telescope you can think of, it is not simply a question of staring at a patch of sky and keeping the telescope fixed relative to a patch of sky and taking pictures. Gaia does not take images. This makes Gaia very different to imaging space telescopes like the Hubble or the James Webb Space Telescopes, which we are relatively familiar with. And one of the key differences is how you get data from the detector. Reading data from CCDs, charge-coupled devices, is a crucial element of the operation of Gaia. So it's worth taking a minute or two to look at how that works for Gaia and how it's different from other systems. When light hits a CCD, the light generates charge, and the question is, how do you measure the charge that's generated within each of these CCD sensors? In other words, how do you go from a whole load of charge that is building up in the detector, how do you go from that to a whole load of numbers that tell you how bright is the object that arrived at this particular point in the sensor? So let's just remind ourselves how this is done in a conventional CCD. When you are imaging a star field, let's imagine we're dealing, for instance, with the Hubble Space Telescope. Imagine a star field. How is the image made up? Well, remember, the image data is just an array of numbers. Light hits the sensor generates charge, and we want to read out what is that charge. So let's imagine we are staring at a patch of sky, so-called stare mode. We expose the CCD to a patch of sky, having fixed the telescope in position. The image builds up, and once the exposure is complete, then the data is read out one line at a time. It goes into a register, and then the register is read one pixel at a time, and the amount of charge in each pixel is measured and stored. Once that's done, the next line shuffles down, and everything else in the detector shuffles down one line. And then again, every pixel is read out. It takes about a millisecond to move every line down, and it takes about a microsecond to read the content of each pixel and convert it from a charge to a digital number, which is then stored. So of course I'm only showing 25 pixels here compared to the many millions of pixels that will be in a CCD. But once it's finished, all of the charge has been effectively drained out of the CCD, and we now have an array of numbers. And because we know how the data was read out, we know which number corresponds to which pixel, and the data itself corresponds to how much light arrived, and hence we can reconstruct an image from that data. That's using a CCD in stare mode, where you point a telescope at a distant object and you try and keep the telescope absolutely fixed whilst you expose, otherwise you blur the image. But Gaia doesn't work that way. Gaia spins, and so the stars drift across the CCD. So how can that possibly work? How come you don't end up with lots of blurred images? Well, for a start, Gaia doesn't take images. So let's imagine that we've got one star drifting down the CCD. As the star drifts down the CCD pixels are read out continuously, and so the star always hits the same pixel. The signal keeps adding up. Once the star reaches the final edge of the CCD, the pixels are read out. When it finds a star, it makes a note of the time at which that star was read out. And that's happening all the time for all the stars that are drifting over the CCD. The CCD is read out. Each line moves down approximately 1 millisecond at a time, and that is a continuous process. The lines are shifted down every millisecond, effectively, for the entire 10-year mission. And it's the timings of the stars that reach the edge of the CCD that is critical in determining where the stars are in space. But let me deal with this idea of 2 telescopes, 1 detector. Whose crazy idea was it that you have 2 telescopes pointing in different directions, but the light goes to the same detector. Well, actually, you've probably heard of this before, though maybe you don't realize it. That's how a sextant works. Now, I'm sure you've probably got a sextant in the boot of your car. I mean, you have to have a backup in case the GPS fails, yeah? Right, okay. So let's remind ourselves how sextants work. You set it up such that you've got a couple of mirrors that can be moved, or at least one of them can be moved, and you point the little telescope at the horizon. If you've got a star in the sky, in principle it could be the sun if you're doing this in daylight, but let's imagine we've got a star in the sky, some angle above the horizon. You adjust the mirror such that the star appears to be on the horizon. In other words, you've got two sources of light going to the same detector, your eye. Now, in the case of the sextant and navigation, it's the angle of the star above the horizon that matters. That angle gives you your latitude via a calculation which we're not going to worry about. But the point is that in this context, the light from two objects is reflected from mirrors so that they appear together on the same detector, in this case, the retina of your eye. So think about what that means. Because they are both in the same position, you're looking at both of them at the same time, it doesn't matter if the deck of the ship on which you happen to be standing is rolling backwards and forwards, because if the horizon and the star move, they move together, because the position of the star is determined by the angle of those mirrors, which can be determined very accurately. If you had two different sight lines, if you were trying to look at the horizon and look at the star when the ship is heaving backwards and forwards, you would never be able to work out what the angle is. But because the mirror brings the star and the horizon to the same viewpoint as far as your eye is concerned, that means you can measure the angle between the star and the horizon very, very accurately. And in the case of the sextant, you read it off very carefully on the dial here. But it's the same principle with Gaia. By looking at stars in two different directions through two telescopes, you can measure the relative angle between those two stars extremely accurately. So that's what a naked Gaia looks like. Mirror 1 on the left, mirror 2 on the right. The mirrors are rectangular, gives us very high precision in one direction. We're not so fussed about the precision in the other direction. The primary mirrors are approximately 1.5 by 0.5 meters in size. Just to give you an idea of scale there, there's some Astrium technicians putting one of the mirrors in place onto the optical bench, the big sort of donut-shaped object that has to be a very rigid structure to make sure these mirrors are exactly where you think they are. Let's have a closer look at the array of CCDs. There's a whole batch of them in the middle that are responsible for astrometrics, meaning timing the time at which a star hits each of those pixels or each of those detectors. Each of those CCDs is that size, about 5 by 6 centimeters, and each of them contains rectangular pixels. Remember, the mirrors are rectangular, so you have much higher precision in one direction than you do in the other. The large direction of the mirror gives you very high precision, so the pixel is 10 microns in width. The size of the pixel in the other direction is not so critical, so they're about 30 microns. About 9 million pixels in total in each of those CCDs. On the right-hand side, there's a couple of so-called sky mappers. These are CCDs which are dedicated to the job of telling which telescope did the star come from. Did it come from telescope 1 or did it come from telescope 2? We have to know which one is producing the image in order to get the calculation correct for any given star that is drifting across the CCD array. After going through the astrometrics, it goes through, the light of the star goes through a prism so that we can measure how blue is the star and how red is the star. It gives us some basic colour information. And for a subset of the stars, the light then goes through a spectrometer to give us a full spectrum of the star as well. Just to give you an idea, there's a few other chips in there. It doesn't really matter. Some of those chips are for making sure the focus, for instance, always stays spot on. And the star direction, in terms of the drift direction for this particular cartoon, is from right to left. And to give you an idea of times, it takes about 4 seconds for the star to drift across one of the CCDs. So it takes maybe a minute for the star to drift across the entire gigapixel CCD array. So let's have a look at the operation to see how it actually works in practice. Here's an ESA video. The two fields of view of the two telescopes are color-coded so we can keep track of which is which. One is color-coded cyan, the other magenta. Let's have a look at what telescope number 1 is seeing. The light hits the main mirror and is folded backwards and forwards until it eventually hits the detector itself, sitting there. So the images produced by that telescope fall onto the projector and will drift from right to left. The other telescope, looking at a different patch of sky, hits the other mirror but ends up on the same detector. But the sky mapper tells us which star is which. As Gaia spins, the stars drift across the detector. Let's follow one star. It's tracked through a CCD. When it hits the end, it's timed as to when it arrived and also how bright it was. Then it goes across the next CCD. Again, when it gets to the end of the CCD, it's timed when it arrived and its brightness is measured again and again and again across the entire field. Multiple measurements. Then we measure how blue is that star, then we measure how red is that star, and if it's in the right position, it also goes through a spectrometer so that we get a full spectrum of that star. To give you an idea of what is actually happening, in this cartoon, we remind ourselves that we're not following one star, we're following all of the stars that are drifting across the field of view. In this case, it's a few dozen stars. But in practice, when Gaia is operational, there might be 500,000 stars drifting across the CCD. And at any given time, there can be thousands of stars that are being read in terms of the timing at which they arrive at a CCD edge and how bright those stars are. So that is how, in effect, Gaia gets its trillions of observations. It's measuring a fraction of 1,000,000 stars at any given time drifting across the CCD array, and it's doing that effectively every second for its entire 5 or 10-year mission. And it's the fact that it's taking trillions of observations, multiple observations of every star, not only when they transit across as indicated by this cartoon, but eventually it'll come round and map that star again some hours or some days later. And it will take repeated measurements of the star positions, and that's how it's able to map out, for instance, the corkscrew motion of any given star in the sky to tell how it's moving as well as its parallax. Gaia spins once every 6 hours. Remember, it takes about a minute or so for a star to drift across the CCD. Gaia does one complete spin in 6 hours, and it precesses as it goes around in its orbit. So that means as it spins in 6 hours, it maps out a ribbon of sky with its two telescopes. But the ribbon slowly sweeps out and covers the entire sky as Gaia orbits at L2 and precesses in its orbit around the Sun. In this cartoon in the bottom right, the darker colours indicates the region of sky that's mapped out more times. The darker the colour, the more times it's been imaged. So not every star is imaged the same number of times. They've tried to arrange it so they get a good sky coverage, and as long as they observe for many years, they will cover every part of the sky to very high precision. So what data was acquired? The original mission was a 5-year mission starting in about 2014, and then it was extended so it became a slightly more than 10-year mission, about 10.5 years in total. The data from these two missions, the original and the extended, it takes a while to process the data. Remember, it's ultimately taking many billions, if not a trillion or so measurements, and the measurements are timings. And from the timings, it then tries to build a model of where must these stars be in order to give me this set of timings, which Gaia has measured to very high precision. It has an onboard atomic clock. So it takes time to take billions and trillions of timings and convert them into a set of coordinates that is consistent with those timings. So data releases came out every few years. 7 data releases are planned in total. Would you call them 1, 2, 3, 4, 5, 6, 7? Well, maybe, but they chose 1, 2, E3, F4, 5 for the data releases. Data release 1 was the first one, of course, and that took the first year's worth of data, as indicated by the red rectangle there, and it gave us the coordinates of many millions of stars. Data release 2, a couple of years later, took the first 2 years of data, and because we have more data, we have more precision. Because we have more precision, we can see more stars and get the parallax of more stars. So now we have the coordinates of not a few million, but of a few billion stars. Scientists were getting very antsy about the data release 3, so they had an early data release. That's the one labelled E. That was the first 3 years of data, which gave us improved precision of the absolute motion, the proper motion of the stars, as well as greater precision of their distances. Data release 3, that came out in 2022, had that full level of precision, but also gave us extra catalogues effectively. It gave us data on millions of variable stars, millions of galaxies, hundreds of millions of stellar spectra, an enormous data resource for understanding stellar evolution. It also, by accident, found a few 100,000 solar system objects that are moving in a way that is not consistent with distant stars. Some of those will be asteroids we know about, some of them were new asteroids. The galaxies were quite useful because some of those galaxies were quasars at enormous distances, many, many billions of light years. At that sort of distance, the parallax and the proper motion can be assumed to be absolutely zero, because there's no way within the precision available any parallax or proper motion could be detected. So if you've got a few thousand quasars in your data set, then effectively you've got fixed points on the sky. They take the place of what used to be thought of as fixed stars, stars that are so distant in the Milky Way they can be considered fixed. Now we know all the stars are in motion, but the quasars take up the role of distant fixed stars as a reference point, as seen effectively from the barycenter, the centre of mass of the solar system. In 2024, there was a so-called focused product release in which the first 5 datas, all of the data from the original mission, the first 5 years worth of data, was released. And that gave a refined analysis for very specific objects, hence focused product release. Amongst other things, they looked at a very crowded region. They looked in detail at what's going on in the middle of the globular cluster Omega Centauri, because that is a very dense region. Compared to, this is simply a ground-based image of Omega Centauri, you can see the center of the globular cluster, which might contain 1 million stars or so, is so dense it's very difficult to resolve individual stars. Even the Hubble Space Telescope has difficulty resolving stars right towards the center. They refined the analysis to try and deal with the situation when you had lots and lots of stars in very close proximity. And by refining the analysis, they actually found something like 500,000 stars that they didn't actually realize were there in the first place. By refining the analysis for crowded regions, the intention is, having got that hopefully now right, they can then go away and say, let's have a look at other crowded regions, for instance, the very crowded region in the center of our galaxy. Now that we've refined the analysis, can we actually get more information about all the stars towards the center of the galaxy? Data release 4 will be coming out later in the year, and ultimately the final data release will be data release 5. I've indicated it way over to the right hand side. It would be 2030, possibly even later than 2030. And these late date data releases will contain the full 10-year data set and will contain, hopefully, many billions of stars with the full precision that Gaia is capable of. Let's remind ourselves what the Milky Way actually looks like. This is the best guess we've got, or the best model we've got, if you like. This is what we thought the Milky Way looked like, and Gaia has confirmed that that is indeed where all of the spiral arms appear to be. We can't be absolutely sure about the spiral arms on the far side of the galaxy compared to where we are here. We used to be in the Orion Spur. It looks like it's been upgraded. It's now called the Orion Arm of the Milky Way. So we are here some 8 kiloparsecs from the centre, or if you prefer, about 25,000 light years from the centre of the galaxy. If we think about what happened in the past, Hipparchus, the yellow dot as indicated by the arrow shows us the extent of the stars that were mapped by Hipparchus. 100,000 stars might sound like a lot, but of course it's only a tiny fraction of the galaxy. So we could only really say what was going on inside that yellow dot. Not really representative of the whole galaxy. Data release 2 of Gaia back in 2018 extended that range so that we could now see a little bit of the arm in which we sit and other regions as well, but still a limited view of the entire galaxy. Data release 3, because of the higher precision that was achieved, allowed us to get parallax from much further afield, and so the reach of data release 3 was much, much larger. In 2022, we have enough data that we can get an idea of stars' positions and motions out to that sort of distance. Still struggling to get real detail of what's going on in this really crowded region in the centre, but it's hoped that data release 4 and 5 will give us more information about what's going on in there. You might have seen this all-sky map before, but remember, this is not an image taken by Gaia. This is a map. Each pixel in this so-called image, actually the brightness of the pixel simply tells you how many stars did Gaia find in that particular pixel of the sky. And so bright pixels simply mean there are lots of stars there. Dark pixels means there aren't many stars there. It looks like an image just because we are effectively counting stars. So let me finish by saying, what did we learn from all of the data that's come out of Gaia? The data so far and possibly the data to come. Well, remember, by getting distances, we can get luminosities. And so a Hertzsprung-Russell diagram in which luminosity is on the vertical scale and colour is on the horizontal scale, Gaia has given us distances, and so now we can map out luminosities accurately. And because Gaia takes red and green as well as spectra, we can get the colour reliably as well. So this is not a cartoon of what we think the stars look like in terms of the population of our galaxy. This is actual data. Every black dot corresponds to an actual star whose luminosity and colour is known. There are so many black dots in the centre, we have to change to a colour system whereby yellow is lots of black dots per square pixel and orange is not quite so many black dots. So each of these dots here is actual data. So we know that this is the Hertzsprung-Russell diagram of stars in the Milky Way, at least this half of the Milky Way. So rather than assuming that's what it looked like, we now know what the HR diagram of the Milky Way population actually looks like. And that allows us to get a much better handle on our understanding of stellar evolution. Along the way, we found a few surprises. For instance, we found a few sun-like stars that seemed to be orbiting, well, nothing in particular. We found stars that even after accounting for their motion around the Milky Way, even after accounting for parallax, they still seem to be making small elliptical orbits around something we couldn't see. That small object was not massive enough to be a black hole, but is thought to be very probably a neutron star, massive but not luminous. And so we have found stars that we can easily see that appear to be orbiting around hidden neutron stars. And we found 20 or so of them, so that must mean there's an awful lot of them out there. And again, the astrophysicists have to do a little bit of thinking to try and understand how can you make a neutron star and leave a sun-like star behind as a companion? Surely when you make a neutron star, don't you have a supernova? Doesn't it blast everything away? Apparently not. Again, we have to rethink some of what we think we understand about stellar evolution. It turns out the Milky Way is warped. This is an artist's impression of what it would look like from the side, as it were. It's not strictly two fried eggs back to back. It's got a little bit of a warp in it. We've seen that in other galaxies. This particular galaxy, NGC 4565, if you look very carefully at the dust lane that goes down the middle, that is actually ever so slightly S-shaped as well. So we've seen warped disks in other galaxies, and so perhaps it shouldn't be so much of a surprise that it turns out the Milky Way is warped as well. And it's warped because of the interactions between our galaxy and others. Not only can we get an idea of how the galaxy is moving in terms of how stars are orbiting and rotating, because we can map out star motions, we can get an idea of how fast the stars are moving and in what direction they're moving. Are they all going around the centre of the galaxy in a nice sedate way, in the plane of the disk of the galaxy, in the plane of the spiral arms? Well, a lot of them are. But there are some that are moving in very odd orbits. Some of them are going backwards. Some of them are going almost in polar orbits. Some of them are looking like they're on very elliptical orbits rather than very nice, sedate, almost circular orbits around the centre of the galaxy. So we come to the conclusion that the Milky Way has interacted with other galaxies in the past by mapping out the velocities and the orbits, extrapolating the orbits of all the stars we can see. We come to the conclusion that the Milky Way has interacted and merged with other galaxies in the past. We can get an idea of the family tree. This is only a schematic, not a real tree. A schematic of how we think galaxies have interacted and merged and finally produced our Milky Way. We've seen galaxy mergers for other galaxies in the universe, so again, it's no surprise to learn that our Milky Way is the product of lots of galaxy mergers. But rather than simply supposing that, we now know that is the case. We can actually map with reasonable precision what must have happened in the past. This is a timeline from the Big Bang on the left-hand side to the present day on the right-hand side. This is a map of interactions that we've had with other objects. I'm not going to talk through all of the details, but for instance, we have interacted somewhere between 11 billion years ago and 8 billion years ago. We interacted with a galaxy called Enceladus, and we think some of the globular clusters that currently we see in the Milky Way actually came from the Enceladus galaxy, which has then merged with us, and we have effectively stolen its globular clusters and some of its stars. The Sagittarius dwarf galaxy here on the right hand side, notice that I haven't capped it off. It is still interacting with us, and seeing what that has done in the past from about 6 billion years ago to the present day is quite interesting. We think the Sagittarius dwarf galaxy has interacted with the Milky Way a little like this. It collided with the edge of the Milky Way 6 billion years ago. It produced a whole load of new stars. It dragged the stars of the galaxy out into a star stream. It interacted with us again 2 billion years ago, and then again 1 billion years ago. So this particular object has interacted with the disk of the Milky Way at least 3 times that we can determine. And it's left this breadcrumb trail, if you like, this star stream of stars that have been left behind by the tidal interactions of this galaxy getting close to the Milky Way. But it's actually quite interesting to note that not only can we pin down when these interactions were by looking at the orbits of stars within the Milky Way, the first interaction, the first major interaction, occurred about 6 billion years ago. And whenever you have 2 galaxies interacting with each other, almost certainly that will lead to new star formation, because the hydrogen clouds in the 2 galaxies will disturb each other, they'll possibly even pass through each other, and that will catalyze or trigger new star formation. That happened 6 billion years ago, and our sun is about 5 billion years old. So it is quite possible that the Sagittarius dwarf galaxy interacting with the Milky Way is the reason the sun was born. We can't pin that down exactly, but it seems plausible that the sun was born at the time that the Sagittarius dwarf galaxy interacted with the Milky Way. So maybe we owe our existence to that particular small galaxy. The idea of star streams, when one galaxy passes close or through another, leaving behind a breadcrumb trail of stars in its wake, we see that with other galaxies. In this one, you can perhaps see the faint star streams. If I change the contrast and invert it, you can see those star streams more clearly. There's definitely signs that one galaxy has interacted and possibly orbited this galaxy and left behind a stream of stars. This is Messier 63. It perhaps looks like a totally isolated galaxy. But if we do the same, invert and bump the contrast up, well, again, we can see star streams indicating that this galaxy has probably eaten other galaxies in its past and left these star streams behind. Even when it's not so obvious, we can still see signs of interaction from the history of these galaxies merging and interacting with each other. The more we look, the more we see this sort of behaviour. So again, it's no surprise that we found a similar behaviour for our own Milky Way. But instead of just supposing that was the case, we now have Gaia's evidence that that indeed did happen in Milky Way's history. Not only can we say something about the history of interactions that have occurred over the last 12, 13 billion years, we can also get some indication of what's going to happen in the future. Because as well as the Sagittarius dwarf galaxy continuing to interact with us in the future, we can also judge from the way things are happening in the stars that we can measure with Gaia, 2 things are going to happen in the next few billion years. We are going to interact with the Large Magellanic Cloud. We can see stars in that cloud. We can map out their velocity. We can see what they're going to do. And also the Andromeda Galaxy. It is quite incredible, but even at a distance of 2 million light years, it is still just about possible to measure parallax of stars in another galaxy like the Andromeda Galaxy. It's right at the limit of what Gaia is able to do, but it's hoped that with the new data releases 4 and 5, it'll be possible to get the precision to the point where we can say definitively, this is the way the Andromeda Galaxy is behaving. We think it's going to collide with us. We're not sure if it's going to be a head-on collision or a glancing blow, but with higher precision, even at the distance of a couple of million light years, it might be possible to get the parallax and hence the distance and hence the motion of these stars in Andromeda to see how we are going to interact in the future. So let me finish with an epilogue. The data acquisition phase of Gaia finished in early 2020 2025, and it was put into a retirement orbit in March of 2025. Remember, for its life, it was orbiting around L2. If you give an object a nudge slightly away from L2, then effectively it just goes into orbit around the Sun, as indicated by the red arrow. So Gaia has now been removed from L2 to make more space for other spacecraft which are going to be joining the James Webb at L2 in the future. As it drifted away from L2, it was actually bright enough to be imaged, and ultimately it will come close-ish to Earth every 14 years or so, so it might be possible to see it again in another 13 or so years' time. Before it was powered down, it sent a last message. You can see there in the bottom right, it was given a whole load of data such that when color-coded, it came back to the Earth controllers as a little goodbye message. Will there be a Gaia version 2? Seems unlikely. Later this year, or perhaps next year, the Nancy Grace Roman Space Telescope will be launched, which will have incredible resolution. You can see the effective size of the detector for the NGR compared to the tiny square in the middle, which is the Hubble Space Telescope field of view. But these will be at the same resolution. So the Nancy Grace Roman Telescope will be able to see an incredible amount of the universe at the same precision as the Hubble Space Telescope, the same resolution. Nancy Grace Roman will work in the infrared, so in principle it'll be able to see parallax of stars that the Gaia Space Telescope finds difficult in the very dusty regions near the centre of the Milky Way, for instance. So Nancy Grace Roman is not a replacement for Gaia, but it may be able to give us parallax of even more distant stars. Gaia is producing shed loads of data. Data release 4 will be an estimated 500 terabytes of data on star positions and star luminosities and star ages and chemistry, etc., as well as their full spectral characteristics. And all of that data is going to be looked at by a whole load of astrophysicists. I'm sure they'll be using some AI tools along the way to help them sift through this enormous amount of data to try and help them build models of how we think the Milky Way is behaving, the dynamics, the evolution, galaxy mergers in the past, galaxy mergers in the future. And because we're getting all of this wonderful distance data and hence luminosity data, which helps us position stars in the Hertzsprung-Russell diagram, that gives us a really good handle on stellar evolution. Hundreds of millions of spectra are buried in that data, and that will give us a really good handle on understanding and helping us understand any misconceptions we might have about how stars evolve. Along the way, we found more information than we were expecting on neutron stars, the orbits I showed earlier. Gaia has also found one of the largest black holes, other than the one in the centre of the Milky Way, out there. We've also found some solar system objects and, by accident, a few exoplanets as well, because, again, any small movement of the star could indicate it's wobbling because of the existence of an exoplanet. When data release 4 and 5 eventually come out, the precision should allow us to perhaps get a good indication of how stars are moving and how they are moving under the influence of dark matter and dark energy, and how that is distributed throughout the Milky Way and beyond. So Gaia isn't just a Milky Way machine, it is far more than that. It's often been described by two words: obscurity and ubiquity. Obscurity because it is nowhere near as famous as its cousins, the Hubble Space Telescope and the James Webb Space Telescope, because it doesn't produce nice, pretty images. But the second description, ubiquity, reminds us that Gaia data is everywhere. Gaia data is being used by every ground-based telescope. Gaia data is being used by every space telescope. Gaia data, one way or another, is going to be used in astrophysics projects, not simply for the next few years, but for the next few decades. Gaia data is Gaia's legacy. Thank you.